graph of the derivative, and it says where would f, which you can't see, have these sort of extrema? You guys figure it out? Are you at impasse? Charles, did you have it? Karen, you have it? I see why. All right, what do you think it is? I think it's A. Who thinks it's A? We got four supporters. All right, should we just take it? Who thinks it's B? Huron thinks it's B. Huron is correct. All right. Do you want to explain? All right, listen.
Derivative, so that would be like 4x to the third or something like that, like something to the third.
Yeah.
So I figured like the original, like f should be like x to the fourth.
Oh, so yeah.
Right?
Oh,
All I
okay.
know is like you would have like ones and
Yeah. Did anybody do? I thought so he was thinking that there would be 3. Right. So like if this is the derivative, this would have 3 roots, right? So the derivative has 3 roots, or 2 like a cubic, right? This 2, like this original would have 3 maxes and mins total. Does that make sense how he's thinking? That a quartic has 4 roots and 3 maxes or mins. It's all foiled out. So he knew that they had to sum to 3. Chris?
I thought that the end, like A, is equal to the minimum. Because it looks like it's equal to the other minimum.
Oh wait, is it A? 1 max and 2 mins.
It's pretty complicated.
Oh, it is A. All right, Jimmy, why were you confident in A?
Because
But Kieran's like it still holds true that like this is 3 maxes. Like A and B are both good contenders because there's like 3 maxes and mins total, which is what a quartic would have. Okay, go ahead, Jimmy.
you look at the root farthest to the left, it has like negative. So if you think about it, that's negative slope of a derivative, so it's a negative slope. So it's going down. And then 0 is when it's a horizontal derivative. So it's like the maximum right there, and then it starts to go up again.
It would be like
There are 2 of those.
it would be a maximum or a minimum right here.
Oh, minimum.
It would be a minimum.
2 of those, and there's only 1 where it goes from positive to negative.
So-
That's the one maximum.
Do you guys get what he's saying?
Yeah.
Some people do, some people don't. I'm gonna say the same thing you said, but just revoice it. So with both of these zeros, so for f has max and mins when the first derivative is 0 or undefined. So at these zeros, your derivative is negative and then positive, right? So that means my original function was decreasing and then increasing. So here, like sort of my original function, if I were graphing x, or f would be decreasing and then increasing. Check. And then here at this 0, f, if I'm graphing f would be like a 0. I'm going to graph it up there. And because this is positive and negative, Jill, tell me what f is doing like here. It has a positive slope, great. So that means f is blanking. And then here, f is decreasing. Okay, if I were to connect them, it could look like changes from negative to positive, that is a min. When the first derivative changes from positive to negative, that is a max. The answer is A. Alright. You're kind of thinking that the original would be a quartic, which would mean you'd have 3. Alright, I'm going to pass these out so we can make some notes on this lovely chart. This chart we will know and love. It will be super helpful. We're going to make some notes on that. I wonder where our cards are. Okay, so on this, thank you. So we're going to fill out some of this. We're going to fill this out a little bit as we learn, whatever we learn on it. We're going to fill it out as we go. All right. So if a function value is positive, that means, what does that mean graphically? Can somebody describe what this means? Thank you. Can somebody describe what this means graphically? If you have a function that's positive, where sort of is it? Charles? From negative to positive. So what quadrants? 3 and 1. If you're positive, if I say my graph is positive, Charles? Yeah, quadrants 1 and 2. Alright? So in other words, positive would mean above the x-axis. Alright? Negative would mean below x-axis. Okay? If you know your original... Okay, I'll let you write that down. Yeah, like the function value, that means like your y value.
It's not the derivative, it's just y back.
It's just y. This is, yeah. All of these are talking about my original function. What is my original function? Here I'm saying my function is positive. If I say you have a positive function, what you're picturing in your head is something that's above the x-axis. If I say your function's positive. You don't know anything about the first derivative or the second derivative. If I say my function's increasing, what does that mean my function is doing? It's going up, right? That's all. That's it. Going up versus down. Okay? This is the interesting one. If I say my function's increasing, let's just stick with increasing. What does that mean my first derivative is? Take a guess. You're all working in pencil. This is great. Write it down. Write down what goes in that next square rectangle box. Oh yeah. Oh yeah. You don't need to write just right. You don't need to write slow base. Because like this being like f prime. Some people are hesitant to commit or just don't know. Nictron. Oh, hesitant to commit. Oh, not that many people know. What do you say? Ooh. Are you Jill? What do you write? Positive. Positive. If your function is increasing, your derivative is positive. I'm going to say that again. If your function's increasing, your derivative is positive. You ready for a call and response? Okay. I'm going to say it, and then I'll say 1, 2, 3, and then you say it. If your function's increasing, your derivative is positive. 1, 2, 3.
Function is increasing, the derivative is positive.
Now, I'm not even going to say it, but say like the reverse of that. If your function's decreasing, I have to say it. If your function's decreasing, your derivative is negative. 3, 2, 1.
If your function is decreasing, the derivative is negative.
Okay. This is like that question, okay? And then you can't say anything about the second derivative. More to the point on this question, Alright, I'm gonna pass these out so you can refer to it. There we go. 1, 2, 3. There we go. Everybody's got one. More to the point, if you have your function having a local max, alright? What a local max looks like is it's the top of a hump. Other words, it looks kind of like that. Or it could look like that. Or it could look like that. Something like that. That's also a local max. Point is that this is the highest thing in this neighborhood, that's the highest thing in this neighborhood, that's the highest thing in this neighborhood. If you're, okay. Now what I want you to do is try to fill out this box. What is your function doing at a local, what is f prime doing at a local max? F has a local max. What is f prime doing? See that once again. If f has a local max, what is f prime doing? It's changing. This is going to be kind of like a mini sentence here. That's true. He does it in a specific way. Yeah. Oh, that's good. You drew a picture. That's good. All right, Hannah answered in words. Charles answered in a picture. Hannah, you go first.
It's positive and negative.
All right, so I'm going to say f prime changes from positive to negative. All right. Charles drew a picture. What his picture look like is this. That's what f prime would look like. Hannah, how do you, wait, I'm going to let everybody copy and then Hannah's going to explain how in the world she came to that conclusion. Alrighty, Hannah, how do you figure that out?
Well, I mean, we did it on the first APQ question, so that's how
Yeah,
I
can you
did
just,
it.
okay, so it was like this APQ question. Yeah,
But the slope, like for a maximum at first, it's increasing and then it's decreasing.
I like those keywords. You say that again. For a maximum, for f,
It's originally increasing and then it decreases.
so that means
It's originally positive and then the slope is negative.
f prime, the slope is positive and then the slope is negative for a max. Does that make sense? Slope is positive and the slope is negative. Go ahead, fill out both of these, and you can't, well, you can say something about second derivative, we're not going to talk about it. So we'll fill this out later. Fill out these two boxes on your own. I think 100% of people in this class can get those next two boxes. This box, that box. a word with no antecedent. I don't like that, okay? You need to be referring to something concrete. Yes, I know, right, I do. So you need to say like f prime is negative, not it's negative. F prime is negative here, so that means f, not it, means f is decreasing. Does that make sense? So here f prime is negative, that means f is decreasing. Here f prime is positive, that means f is increasing. That means f has a local min. F prime has a 0, f has a local min. That makes sense? Here f prime is positive, so f is increasing. Here f prime is negative, so f is decreasing. That means f has a local max. Okay? F prime is a 0. I think we've beaten APQ1 to death. But it's a really good problem. It's a good one. Alright, we get a theorem. Alright, this is called Rolle's theorem. This is a special case of a big theorem we learned, but you do need to know this special case. Alright, so I have 2 points. Just look at this diagram. I have 2 points, A and B. What do you notice about A and B? Charles notices something. Madisyn?
They have the same y values.
I love that. Say it again.
They have the same y values.
Okay. And what do you notice about, so what would be the slope between A and B? What would be the slope between A and B? If you were to take the slope between them, Hannah?
0.
Great. The slope between any 2 points with the same y value is 0. That means Rolle's theorem says if you have 2 points with the same y value, it's going to be on the next slide, okay? It's written there. If you have 2, but we're just going to talk about it verbally first and then we'll worry about the writing it. If you have 2 points with the same y value, then somewhere in between them on this interval, somewhere in between those 2 points, you'll have a tangent line with a slope of 0. In this case, it's halfway in between. It's not always going to be halfway. Is that your question? Oh, does not always have to be halfway. Because I could totally draw this like that, you know. And but the point is that somewhere over that interval, it could be multiple places, right? It could be, you know, I could have multiple places where the slope is 0. Okay, but at least one spot in that interval, I have a slope of tangent line 0. Okay, so I would definitely have at least one spot. That's Rolle's theorem. So let's read this and so if f is continuous, you have to have a continuous interval, and you have to have it be differentiable. If you're not continuous and differentiable, it doesn't apply. So by the way, differentiable, so like if you have an interval with a corner, you can't apply Rolle's theorem, right? For instance. Okay? You could write that down or not. But if you have an interval with a corner, like you can't apply this because it wouldn't be differentiable. Alright? But anyway, and you have f of a equals f of b. That's what Madisyn said. You have 2 y values that are the same. And there's at least one number in C such that f prime of C equals 0. Okay, we have some in other words, but I think we talked it through, so I'm not going to read that. Right. Blah, blah, blah. Ooh, this is also it's corollary. If you start and end at the same y value, and at some point in between, you must hit a max or a min. You know, because like that's when the derivative equals 0 is a key place. That means that you're probably gonna have a max or a min, right? Unless, or you already yes, Charles.
Just like what?
Great counterexample. So, right. So this is a counterexample. This is why. So this does not say relative max or relative min. This says absolute. I mean, this just says max or min, so that means absolute. So you do have a highest value in this interval, even if it's flat. But you don't necessarily have to have a relative max or min. Okay. Example of Rolle's theorem. So we're going to do this together. So sometimes this is one of those cases where it might be an open-ended question, and you're going to have to prove something. So these aren't always multiple choice, although they often are. But sometimes you have to like prove it in work. So Chris, can you read this, please?
Find the 2 x-intercepts of f of x equals x squared minus 3x plus 2. And show that f prime of x equals 0 at some point between the 2 x-intercepts.
Go ahead, find the x-intercepts. And then we'll do the proof together. you should have gotten 2 and 1 as your two x-intercepts. Here's how you show it, all right? Here's how you show it, since, okay? Now, for Rolle's theorem, again, let's refer back to that picture we have in our brain and what Madisyn said. You have to have 2 y values equal to each other for Rolle's theorem, right? So I'm going to say, and then we just write our proof is a sentence. So since f of 2 is the same as f of 1, because they're both equal to 0, okay? Since those 2 y values are the same, they're both equal to 0, all right? But it doesn't matter, they could equal the same anything. They could both equal 17, you know? Like as long as they're the same, you apply Rolle's theorem. So since f of 2 equals f of 1, by Rolle's theorem, so you don't need to say specifically it's continuous and differentiable. If you apply Rolle's theorem, it knows that you're citing as continuous and differentiable. By Rolle's theorem, there must exist, find the two x-intercepts and show that f prime of x equals 0. Alright? There must exist, and so I'm going to use that here. There must exist an f prime of x equal to 0 on what interval? We need to cite the interval. What interval? Somebody not raising their hand. Brian. Yeah. And you do include the endpoints on what count. So that's Rolle's theorem. Alright, this guy? Alrighty, that's all we need to know about Rolle's theorem. We're moving on. The mean value theorem, I love this. It's so important and comes up so often. It's got an abbreviation, MVT. You know that that's the big deal then, since it's called MVT, you know. Alright, Mary, can you read this so far?
If f of x is continuous over the interval ab and differential over ab and at some point c between a and b.
Here, and then here's the so that's the hypothesis of the theorem. Here's the actual result of the theorem. Bam! Okay, and have you write down on the top? F prime of c equals f of b minus f of a over b minus a. It's a great result. Okay. This should not look like a crazy formula. It should not look crazy. This actually should look so simple you're like, how is this a big thing? This is just saying that the derivative equals the slope. You know? Right? That's like all this is saying. That's all this is saying. Alright? In other words, this means that at some point in a closed interval, the instantaneous slope, is that derivative, is that the left side or the right side? Instantaneous slope. Is that talking about the left or the right side? Charles? Yeah. Derivatives are instantaneous equals the average slope. That's like, this is how you write an average slope. That's all it's saying. Okay? But let's look at that. We're going to look at it as a picture. But it is a pretty big result. Alright, so let's look at this. So another way to say this is that average, yeah, Chris.
Go back to that slide.
Yeah. You want to see the words underneath? Oh yeah, let's give you, these words are good. This helps you actually learn. In other words, this means at some point over a closed interval, that's cool. But this is the big result. The instantaneous slope, aka derivative, equals the average slope. And it's like Rolle's theorem in that you have, like, over an interval, you're guaranteed to have something specific happening. If you know basically what this is saying, well, we'll look at the picture. So it'll help with the picture. So if you look at the picture, so you have like 2 points here. The slope of the secant line is like the average slope, right? Secant lines give you an average slope. So if I have this here, look at the slope here. This says that somewhere on the interval from A to B, I have an instantaneous slope. In terms of a picture, what's a different word we can use for instantaneous slope? slope of what? For instantaneous slope, you could say the slope of, it's like the slope of what? In terms of on a graph. Charles? It is the slope at a point. Yeah, there's a special word, there's a special kind of a function that's a slope at a point. I mean, besides derivative. Charles? Oh, you're going to say derivative. Yeah, this is derivative. That's just like not what I'm fishing for a specific word here. Clearly, people aren't like catching my line I'm trying to throw out. Madisyn?
Slope of a tangent line?
Yeah, slope of a tangent line. Alright, so average slope is the slope of a secant line, slope at a point is slope of a tangent line. So basically, on this interval, and I think my slide gave it away, there's one place here where if you draw a tangent line at that place, it'll have the same slope of the secant line. Let's do that. So right there, if you draw a tangent line here, notice how C is in between A and B. If you draw a tangent line here, and the slope of this line is the same as the slope of that line. AKA they're parallel, right? That would be another way to say that. They're parallel. But this, so a third way to say this, okay, so on the previous slide we have two different ways. A third way to say this is the slope of the tangent line equals the slope of the secant line. That would be a good graphic way to say the MBT. You have the slope of a tangent line somewhere in the interval. You can draw a tangent line such that its slope is the slope of the secant line. Again, just like Rolle's theorem, you can have more than one place. We'll get to that, some examples of that later, but like you'll definitely have at least one place. Okay, well, let's do, see what a problem is. Looks like we're already doing a problem. This is great. ABQ2, wow. Okay, the mean value, let's have Kieran. Go ahead, Kieran.
The mean value here guarantees the existence of a special point on the graph of y equals square root of x between 0, 0, and 4, 2. What are the coordinates of this point?
So this is great. It tells you explicitly to use mean value theorem. So I'm going to copy down the theorem to start the problem. Okay? I'm going to say f prime of c equals f of b minus f of a over b minus a. So I'm going to have you do this on your own. We will go over it, probably, unless everybody gets it, or most everybody gets it. So the derivative equals the average slope. This is your function. You're going to take the derivative. Okay, so I'm going to walk you through the problem, and then you're going to do it. You're going to take the derivative of your function. Your derivative will have an x in it, right? Okay, so you're going to have an x on this side, a derivative. And then you're going to take the average slope. Average slope, that's going to give you a number, right? And so you'll have an equation, and you solve for x. That's it. So you don't need to worry about the c so much. Just keep it as like x on the left. That is not f prime. You need to take the derivative. So that's f. Yeah. So you're given f. You need to take its derivative. Set that equal to the average slope. So derivative equals average slope. So use these points to find the slope. So that's the left side. And you set that equal to an average slope. So the equal to, and then use these points to do like, that would be 9 over there, so you put 2 minus 0 plus 1, 0. You do these points right up there. Okay, so I'm going to have you write on the board up until there. Just got ready to go to her. Okay. So 2 is so that's the right side. The left side is the derivative. Oh, you did that. Oh, yeah. This is just an equation, but it's an equation. You lost the equation for a bit. So it's that equals that. Okay, yeah, so it's you want, this is good, you want to do that as x on z. Like x to the negative 1/2 is equal to x. And then you set the values here, so those two are equal. Okay. So we're somewhere, you could solve it, you know, you might be solving it a little bit differently, but here's the point. Okay, so we're going to finish the problem together. A lot of people are halfway through, which is, you know, it's actually the algebra that is a little tricky here. So the derivative of the function, this is the derivative, yeah? I think and that's the average slope. The mean value theorem says those are equal, okay? So you might have rewritten already, you might not have. She didn't rewrite, she actually got multiplied by 2 on both sides to get rid of the halves. So now she has this, pretty cool. Now we'll rewrite, or actually, can you just think of what x value would make this true? Just think in your head, what x value would make that true? Somebody who's not Charles, because Charles is like answered 2 questions so far. What x value would make this true? 1 to an exponent equals 1. Chris? 1. That makes sense solving that? Okay, so we just solve that mentally. And, oh! Look at this. What point's it probably going to be? Beyond. B. And then to get this y value, you just take 1, plug it into here. The square root of 1 is 1. Like if there were multiple things with the x value of 1, or you wanted to make sure it's at e. So, sweet. So that's the mean value theorem. Think of it also, so we did a graphic example that was conceptual, but you can also just think of it as literally an equation that you solve. Most of the problems are going to look like that. It's an equation that you solve with the derivative equaling the average slope. Jimmy.
It said like in the question it says like a special point. So does that mean like 2 integers, like 2 numbers?
No, that's not why it's special. Here's why it's special. Let's see why it's special. So if I take, okay, I'm going to graph a square root function. So I go up 1 over 1, and then I know the square root of 4 is 2. 1, 2, 3. So I'm graphing that, okay? Okay. So I know that my average slope looks like this. So what the mean value theorem says is where along this interval can I draw a tangent line that's parallel to this? You know? And our answer is 1, 1. So would you say right there, if you were to draw the tangent line, it would have the same slope as that secant line? That's why that point is special due to the mean value theorem. Okay? Good question. Alrighty, do this on your own. Totally on your own. Okay. The final answer is really tricky to come by. Yeah, so find factor of 3. Yeah, you have to plug in. Yep. Okay. Alright. I know, a lot. So if you get the answer and then you're not sure, you know, there's kind of like 2 choices that look good. You're not sure which choice to choose, we'll talk about that. So you got the values, yeah. So you have to find the y values based on the limits, so you put in 0 here. Oh, you should put 0, and that's how you get the number.
Yeah.
Does that make sense? Like, you need y values on top that correspond to these x values. So you use your order to figure out these values. Alright, can somebody summarize for me? This was tricky. Like, how do you figure out the numerator here? Hector.
Just plugging the b and the a to the equation.
So you end up, those are